Hi, everyone. This is Diana Sinton, the Executive Director of UCGIS. Welcome to our workshop today. This was one of the workshops from our original symposium that would have been going on in Hawaii in May, but as you know, things have changed. So we are very grateful that we have Mehak Sachdeva from Arizona State University, who's going to offer this workshop. People are still logging in right now, so we're going to wait for a couple more minutes to get started. What we're going to do, because it will be a relatively small group, and it's nice to be able to ask a real question, so a question with your voice and not just typed out. So once people get started, what we're going to do is I am going to unmute all of your microphones from my end of things, which means then you'll have control over your own microphones, and you would be able to you could raise your hand. So you'll have three ways of posing a question. You would be able to raise your hand with a little hand icon. And our colleague Peter Kedron from Arizona State is also going to be joining us during this workshop, and will be able to make note of the fact that you've raised your hand. You would be able to type a question into the question space, and that would be a way that you would also let Peter know that there's something that you wanted to address directly to one of the instructors, or perhaps about the topic in general. But then again, I will unmute you. You would be able to have your own, control your own microphone. Please keep it muted, yourself muted when it's not being used, to be able to minimize any kind of background ambient noise. This session will be recorded for consultation later. And I know that Mehak has sent everybody copies or an email with lots of other information. So what I'm going to do now is I'm going to pass the baton over to Mehak, and I will mute myself, and then I will also at that point go into unmute all of the attendees so that you can then control your own microphones.
Great. Thank you so much, Diana, for the introduction and for all the technical notes. Hello, everyone, and thank you for attending this workshop on Multiscale Geographically Weighted Regression, or MGWR, hosted by the UCGIS Symposium 2020. I'll just get started, I guess, as people enter in. I'll just go slow in the beginning, and then we'll see if more people enter as the minutes go by. So this workshop is designed to introduce participants to the concepts of local modeling, spatial associations, and spatial process scale using the framework of MGWR. I'm going to assume through the workshop that participants are essentially unfamiliar with these concepts, and start with building and understanding into these building blocks for the framework of MGWR. So if you've already used MGWR and you're familiar with how it works, or if you've used in your research previously, just bear with me through these conceptual slides, and hopefully you will gain something out of it too. As Diana has already pointed out with some technical notes, I will just reiterate by saying that you can be on mute for the entire workshop, or you can choose to interject me with questions as you feel comfortable. At this point, I also want to introduce Professor Peter Kedron, who has very kindly volunteered to keep a track on the questions in the chat box and in the questions box, and raised them to me as we proceed. Professor Kedron is an assistant professor at ASU and teaches a brilliant course on spatial stats. Thank you so much, Peter, for joining. So hopefully you should all have received an email from me yesterday with a resource link and a link to download the software that we will be using today. If you did not have a chance to do that, or for some reason if you did not get the email, I'm going to put those links again in the chat box for everyone. Let me go ahead and just do that. So the resource link is basically what will lead you to the screen that you're looking at right now as I've shared my screen. That is essentially the entire contents of the workshop. And the second link is to the software, where you will be able to download the software for your system, whether you're using Windows or Mac. So I will be walking through the resource page of the workshop for all the conceptual parts. But while I am doing the workshop examples part of it, I will be doing it live. So at that stage, you might want to exit out of the full screen mode that you might be and put that on the side of your screen so that you can follow along with me if you want to. That is why I had written in the email that it would be helpful to have a two-screen setup, but if it's not a problem if you don't. Also, as Diana pointed out, there will be an email sent to participants with the recording of the workshop. So don't stress if you cannot follow it along and just want to view the workshop as I do it. Great. I think we're already at 11:06 or 2:06 for Eastern time. So I'm going to jump right into the contents. Hopefully the link that you would have opened would have led you to this page. You have my contact information here, and I'm always happy to answer any questions that you may have over email later also. So please feel free to email me with any detailed questions. The field and the framework that we're going to talk about today is so large that it is impossible to hit on every minute aspect of it. And even though I would wish to, it is not possible to do that in 2 hours. There are some topics that I will allude to, which would have been covered if this was a full 4-hour workshop as it was intended to. But at the same time, I'm happy to answer any questions or any collaboration thoughts if you may have, if you want to email me after the workshop. So these are the table of contents is where the different pages are, and I'm going to walk through them one by one. If you want to also open that link, that'll be helpful. From number 4 onwards, where we will actually walk through an example data set, but otherwise you can just look at my screen and that would suffice. Great. So to start with, I'm going to start very broad and then narrow down into the problem. The spatial data that we observe in the world around us are basically manifestations of underlying spatial processes. So spatial data is here, and there are some underlying spatial processes that are affecting the data that we observe in the world. Those spatial processes are not visual, they're not measurable, and you cannot basically easily tell the magnitude of what those processes are and how they are affecting spatial data. So we have to model those. In a sense, we have to model the spatial associations that can then be inferred as the spatial processes that form those spatial data. So I know this may have seemed very, very abstract to some people. So I'm going to get into an example soon. But just as an underlying thing is whatever spatial data that we examine, say it is house prices or crime rate in a city, that is the observation. That is the observation data set. And when we want to ask questions of why things are the way they are, why are crime rates higher in some places in a city versus not, we want to understand the processes that are leading to that data that we observe. So it could be unemployment rates that could be leading to higher crime rates, or it could be certain placements of law enforcement areas that could be leading to that. So those are the spatial processes that are affecting the spatial data that we observe. Now getting into a super simple conceptual example, if you look at the New York skyline, the Manhattan skyline, you clearly observe that there are high-rise buildings in the downtown area where the One World Trade Center is, and there are high-rise buildings in the Midtown area. But in the area between the two, essentially, there is a dip, and there are only middle-rise buildings in these areas. Now, this could be an observed pattern that you observe, and you want to ask, why do the buildings in downtown and Midtown Manhattan are high-rise, and the ones in the middle are not? That is a perfectly good question to ask when you look at a spatial pattern like this. Now, there are some processes that are affecting this clearly. Those processes could be air rights. Those processes could be financial in nature. There could be many reasons why we see this pattern as it is. So in this particular example, I mean, I read this through blogs, and this is not to any research, so please don't quote me on this, but this was a good way to explain an abstract concept like spatial patterns and processes, so I'm doing that. If you look at the bedrock beneath Manhattan, you clearly see that the bedrock basically dips in the area between downtown and Midtown. So if you were to build a high rise in this area, you would have to put the foundation of that building way lower, which would be very costly and would actually not turn out to be cost efficient if you were to even sell those apartments or commercial spaces. This is an example of a spatial process like geography of that borough that leads to the spatial pattern that we observe. So here, the uneven distribution of the bedrock in Manhattan led to the observation of the patterns that we see. Another example, which is more pertinent to the social sciences, is human migration, for example. So if we observe mass human migration from one city to another, and we want to understand why that could be happening, we would want to analyze many processes that could be leading to it. So is there a political conflict in a city, or is there lack of natural resources like water or something due to climate change, or is there restrictive policies on financial employment gains that people want to move to another city for better employment? There are many reasons that could be leading to a problem like human migration. So those are the processes that we would then be modeling to understand this pattern that we see of people moving from one city to another. This example also brings to the forefront the issue of spatial scale. So all the processes that affect a spatial pattern operate at different spatial scales. So for example, people moving from one city to another could be led by, as I said, political conflict. That could just be at a city scale. But if it is led by a process like climate change, that is essentially a global phenomenon. And if it is something like unemployment or fiscal opportunities, that could be something at a regional scale through government policies. So the scale at which the process is affecting the pattern is also extremely important. And often it becomes very important to model that scale, not only to understand how the patterns are being affected and at what scale from the process, but also to model the patterns correctly. Because often if we do not understand the scale of the processes and how they are affecting the pattern, the model can be misspecified and the patterns could not, the processes would not make sense. So this is another important example of how spatial processes affect the spatial pattern under examination at different spatial scales. Hopefully people can hear me clearly and are following along. So unless there are any questions, I'm just going to keep moving forward. So the models that we often use to estimate the relationships between processes and patterns they fall under the regression framework or the umbrella of regression. So how like a spatial data pattern is affected by a process is modeled by a regression equation. So in this workshop, we are going to work through a housing price model example. So I'm going to get right into that kind of regression, which is also a subset of all the regression models that exist. But I thought it just might make sense to get into the specific example that we're going to talk about so that you get one full view of from start to end of what that example would look like. So for example, if you have a housing unit in any city and you always know the cost of that housing unit, you know that this house costs so many $100,000 or whatever it is. But it is often not obvious to understand what is the marginal cost of each of the attributes of that house. So for example, what is the cost of a bedroom in a house, or what is the cost of addition of a bathroom in a house, or if you live somewhere like in Arizona, what is the additional cost of a house if you just add a swimming pool in your backyard? So to get to that, to understand the marginal cost of each attribute of a house, we often use something called the hedonic house price model, which is basically a regression equation that isolates the price of each attribute and understands how much of your house price would increase if those attributes were to be added or subtracted. So to put it simply in the form of an equation, this is what your equation would look like. So y is your house prices. That is the spatial pattern or the data that you're trying to examine. So that is your y, that is your dependent variable, which is being affected by many processes. Those processes are your independent variables or the x's in this formula. So that x can be living area or age of a structure, or as I said, addition of a swimming pool. And the beta, this is the measure of that spatial process. This is the measure of how that x is affecting your y. So for example, if this beta here, so if we have y as house prices, x as living area, and your beta assumes a value of 5. Once we put it in the model and it gives us that a beta is 5, what that would mean is that 1 unit increase in your living area of the house would increase your house price by $5, for example, whatever the unit of your housing price is. So this is a very effective way in understanding, how our independent variables or process or just other reasons that we are looking at are affecting your dependent variable, or in this case, house prices. So this is called the hedonic house price modeling, and this is just what we would be using in one of the example data sets that we would do. So essentially in this equation, if you begin to notice, what is happening is that y could be a mix of, or y is basically an array of house prices for a lot of locations in your study area. So if your study area is a city, y would be house prices of all those houses in a city, and x would be the living area for all those houses in the city, and your beta would give you one single estimate for that entire city. So it would say that no matter where your house is located, 1 unit increase in your living area would increase your house price by $5. Now, I think we begin to see what the problem with using this equation in spatial data would be, right? Because that usually never, in real data, that never happens, that your process is affecting the spatial data in the same constant way across your study region. That is almost never true. So just to put it more graphically, let's say that you are doing a house price study in New York City. So this is a map of New York, this is Manhattan, and this is Staten Island, Brooklyn, Queens, and Bronx, of course. So yellow is basically that one beta estimate that you would get if you use this equation. So that beta is constant across your entire study region. So that would basically be interpreted as that if you increase your square footage of living area in downtown Manhattan, that would increase your house price by the exact same amount as it would increase in Staten Island. Now, if you're familiar with New York City, or if you've ever visited, you would know that obviously that is misspecification of facts, right? Downtown Manhattan, the space is valued so much more than in a more suburban and more where there is more area, like in Staten Island. So this is what global regression would give you, like a global regression model such as ordinary least squares regression, if you've ever heard of that before. That is what would give you one beta estimate for your entire study region. What we actually want, or what would be very helpful to have, is a parameter estimate for each location of your study area. Like I would want to know if if the marginal cost of space in downtown Manhattan is different from in Staten Island, and by how much, because my data is actually more granular than that. I'm not looking at just one data point for the entire city. So I should be able to get to that, right? So ideally, we would want a map like this, which would tell me that if you increase your living area in a house in downtown Manhattan by 1 square foot, your price in downtown Manhattan would increase by $1,600, whereas in Staten Island, it would only increase by $450. Now, this makes a little more sense, right? And this begins to provide us so much more information than what we were seeing here. Now we begin to understand what is the marginal cost of living space in denser and more economically affluent places like downtown Manhattan than not. And these have implications and interpretations in so many different regions and spheres. So how would we get to this? This is the scenario that we want. And of course, the more granular your data is, the more information then you can get out of that. So right now we are looking at census tracts in New York City. But if you had point location data for each of your houses, you would get a point estimate for each of your of the city, and that would tell you if your house was here versus if it was just 2 blocks down, how would the marginal cost of space affect your what is the marginal cost of space in that case. And here we are only looking at one variable, which is square footage of living area. This could be many other variables. You could, so this is, here I'm talking about a univariate regression where there is only one independent variable, but you can add as many variables as you want in your model. I mean, then it has restrictions, of course, and then we can get into more technical things in a little bit. But there can be multivariate regressions where you start to add other variables such as age of a structure, or if it's close to a subway station or not, and if it has access to public schools or not. So those kind of factors, of course, affect your house prices. So that is what we would then do. So this is the kind of an output that you would get out of a local regression model, for example. And this is, of course, do not fall prey to this map at all. Sorry, this is only done for representational purposes, but it gives a good picture of what I'm getting to. So now we will get into geographically weighted regression and multiscale geographically weighted regression. So geographically weighted regression, or GWR, is an example of the local regression framework. So basically what it does is that it provides you a parameter estimate for your process at every location in your study area. So how does it do that? For an OLS model, global model, you could only get one parameter estimate, but with GWR, you're getting a parameter estimate for each of your locations. So how it does that is that it basically calibrates a model at every location. So in the equation that we previously saw for the global model, we did not see this particular aspect. This is the aspect that defines the location. So you get a beta for each location, which is an I, in your entire study region. So this is your study region, and if you basically use a GWR, it would calibrate a model at each and every point of that study area. Now, the obvious limitation is that for doing that, we would need a lot of data at the same location, right? Because just for one location, how can we calibrate a model if we do not have more than one data point at that location? And that kind of data is almost never available, where you have at least 100 data points at that exact location, right? I mean, that kind of data almost never exists. So how GWR gets around that problem is by borrowing data from geographically neighboring locations. So this is in accordance with Tobler's law of spatial dependence, that near things are more similar than farther things. So how this does is that if I was to look at, say, for example, this diagram. So if the red point is where I'm calibrating my model right now, I would depend on neighboring data points to provide me with information that I need for that calibration. Similarly, as my point shifts here, it would take neighboring values for that point and calibrate a local model at that point, and so on and so forth. So this kind of a thing would be done for each and every point in your entire data set. So your data around the calibration point are being weighed and used in your local model calibration. So this is how GWR basically gets around the problem of not having a lot of data points at the same location. So now the number of points that are being used at every location to calibrate that local model tells us something, right? So what that tells us is that, whether the process is heterogeneous or is it more homogeneous. So if it was using very few data points, that would tell us that, okay, to calibrate a model, only a few data points are enough, and that those parameter estimates would then change radically between small distances. So the number of points that are being used to calibrate a local model is an important parameter that we get out of modeling with GWR. That parameter is called a bandwidth, and that is used to, that is interpreted as the scale of the spatial process. So right now, if this is your entire study area, and you would see that this is a fairly regional scale or regional to local scale of data that we are using to calibrate model at this point. So this is what translates to what is the scale at which your processes are affecting the spatial data that you want to examine. To get into more detail, this is a visual representation of how your data would be weighed. So if this is your calibration point, all within the circle are all the data points that are being used to calibrate that local model. Again, as the point shifts, there is another circle built, and that happens for every point in this entire study region. All those data points within the region are not weighed equally. They are weighed from 0 to 1, and they diminish as your distance increases. That makes sense, right? If you want to calibrate a model at this point, you would depend a little bit more on closer data points than you would on farther data points until it stops mattering, and then you don't depend on these gray points at all. So this is basically how a spatial kernel or weighting function works in GWR, is that this circle of weighting follows this kind of an approach where the closer data points are used way more than the ones that are farther away, and then beyond that they are not used at all in the local calibration. We will get into a little more detail once we are using the software, because that is where those options are available about the function that you may want to choose and what interpretation of the bandwidth parameter do you want to use. But just conceptually, it is valuable to understand what I mean by the weighting function here. Again, so this is the bandwidth parameter, and in GWR, which was the only tool available in the GWR framework until 3 years ago, there was a bandwidth parameter that could be found for the entire model. So there would be one parameter estimate for all the processes that are affecting the data. So as we saw in the human migration example, that's not true, right? I mean, all processes tend to affect the spatial data at possibly different spatial scales. Some could be regional, some could be local. So we want the flexibility that each process that is affecting the data has a different scale to it. That is where MGWR, or multiscale geographically weighted regression, comes into play. So suppose, for example, if you have all these different processes affecting your data, your bandwidths would vary. This is essentially a global process. There is no variation happening at all. This is a very local process where just moving one block away, your values change extremely. So for these kind of different processes, you would need a different scale or a different bandwidth parameter. So in MGWR, when you do a multivariate regression, multivariate local spatial regression, you are able to find a process scale for each of the processes that are affecting your spatial data. So this becomes very valuable, because if we were using just one bandwidth parameter, that would be an average of all these 4. So it would basically be much larger for these processes and much smaller for these processes. So now with this, we can actually find out the exact scale of the process that is affecting our pattern. I got into a little bit too much of methodology, but it helps to have these kind of background information in mind when you are working with the software, because there are all these different parameters that you can adjust in the model, and you can, it is very customizable according to the problem or the data set that you're trying to use. If there are any questions, I'm happy to answer at this stage. Otherwise, the next part is where we will be getting into the data set and trying to do the fun things. Okay, great. So at this stage, I think it'll be helpful for the people who want to follow along. Here is a link to the example data set that we will be using in this example. And hopefully from the link of the software in the chat, you would have already downloaded the software. If one of these links is not working, or if you need any additional help, please interject, and I'm happy to help out. So the data set that we are using for this example is a house price data set for King County in Washington. It was obtained from an open source Kaggle competition. Basically, that is a great resource for all kinds of data sets, if in case you didn't know. And it is an open to use data set. So that was about 20,000 points across the King County, entire county for Washington State, where you see cities like Seattle, Bellevue, Redmond. It's a very interesting area because there are a lot of technology related jobs that have recently, or in the last 5 to 6 years, that have been added in this area. And there has been a lot of upheaval in the housing market because of that, because it has employed so many more people. It has caused local and international migration, and some areas where there are jobs have risen more than others. And it's a very interesting area to understand how the housing market is being affected. So this data set is from 2016. So there are 20,000 individual data points, which I have aggregated at the census tract level. This is not ideal. Of course, if you have individual data points, you would always want to use that because it has so much more information and it is a way more accurate model than an aggregated model, especially at an administrative unit. But this is only done to simplify our size of the data set and to make it work faster in a workshop setting. Right now, this model with about 350 census tracts fits in a minute and a half. But if you were to use all 20,000 data points, MGWR requires around 5 to 6 hours. Yeah, it is a little bit on the higher end in terms of calibration time, but that's because, as you can imagine, at each point a local calibration is happening. So for all these 20,000 points, you would calibrate a local model. But anyway, so this is the aggregated data set that we would be using, and all the prices and all the structural attributes of the housing data points have been aggregated at the census tract level. So once you click on this link, actually I'm going to share a non-clean version of my monitor so you can see. The moment you press this link, it should automatically download in your system. So wherever you've defined it to be downloaded, say this goes into my downloads folder here. It's in the downloads folder, but for you, it may be someplace else, wherever your system downloads files from the internet. So if you open the data set, you should see something like this. This is a snapshot of the table that you would see. It's a CSV file. So you would see that there are many columns in it already, and I have already made some transformations that I will be talking through because it's just easier to not have to go through data cleaning and aggregating when that is not the point of the workshop. So houses are the number of houses that were in each census tract that were taken to average the parameters, and then there are all these different columns that I'll talk about. So the dependent variable, as we saw with the New York City example, or as I've been talking about in the regression equation, would be the average price. So this would be the average price of the houses in each census tract. That would be our Y value. And that is what we want to understand and how that is being affected by these different attributes. So for housing prices, they could be, whether there is unemployment in that census tract or not, whether, so as you see in this area, you see so many water bodies. In the Seattle region, there are a lot of waterfronts. So a major reason why housing prices are higher in some places versus not in this county are because of the access to waterfront. So if your house is right on the lake, of course, it's going to be valued a lot more than if it is, somewhere down south here where there is not much happening around. I know these have been aggregated in the census tract and I've not removed the water layers, but because, on the edge, they still have houses. So you see that all these, even though they are water bodies, have a high average price because there are many houses right on the edge that fall inside that census tract. So unfortunately, that is another problem that we have with aggregated data sets. But so it's very helpful to know the context of your particular research problem before starting to understand the variables that you might use. So this is one of those examples where I was telling you in the beginning that if this was a 4-hour workshop, ideally I would want to go through this part in much more detail that I'm going to right now, which is about variable selection. So I think that is one of the most important parts of any regression modeling, especially because your model at the end of it, when you publish a paper, looks great, and you somehow feel like all these variables are making sense when you start to interpret them. But it is a long process to get to that. And that is essentially driven by literature reviews and how theory, like, tells you about some variables that have been found over time to be significantly affecting the pattern that you are trying to observe. So hedonic house price modeling is a very, very well researched topic. You will find papers from decades ago, and they have understood, how house prices are affected in many different places in the on the planet and in different countries. So there's a lot of literature available, but of course, like I said, context is also important because we are doing spatial regression. Especially, we want to be cognizant of the geography that our study area is in, and then we want to inform our model making using those variables also. So using the 20,000 data points, I have we have already published. We have already done a paper, and which is under review. And the model that I used for that paper is the model that I'm going to use in this workshop. But ideally, it would have been a lot more fun to go through that process together. But unfortunately, we won't have the time right now. But I'm happy to take any questions on email or otherwise if you want any tips or tricks, or if you want to collaborate, if you have any questions about your own research and are not being able to understand what variables to include and to exclude. There are many technical reasons why you would include or exclude variables, and I mean, it's as much of an art as a science. And but essentially, your entire problem should have a hypothesis behind it. The models that basically just do like those, run with 100 variables and select 5, I would be very wary of that approach. So basically, it should be informed by literature, and it should be informed by what is the question that you want to ask. So in this particular model, which I mean, now because we're using aggregated data set and that is not in the picture, with this data set, what we wanted to ask was that, is there like, a preferential treatment of a neighborhood in the county where, so basically what we were trying to get to was, is there a locational preference that people have beyond all the structural and neighborhood attributes for house prices? So is it just because that people want to live in downtown Seattle that they would pay extra, even though the house would have the exact same amenities and the exact same waterfront view as some other house? And that was interesting because you can get to that local, interpretation with individual data points. But that kind of a question is harder to do with aggregated data set. So unfortunately, I'm not going to walk through the hypothesis formation and variable selection parts of regression, which are extremely important and also very interesting. So just bear with me that this is the model that we will be using, but I'm happy to, of course, answer questions, as I said. So these are, the dependent variables, there are 2 columns in your data set, getting back to that. They're called average price or natural log ln average price. Why we would want to do that, I will get to that. But so that is just the average price of houses in a census tract. Then there are several independent variables, such as average number of technology jobs in a census tract. Then there are average unemployment, which is the average unemployment rate in a census tract. Then average index, this variable is what we made for the individual data set. This measures the number of houses that have a view to the waterfront. So just being next to a waterfront and having access through distance is not the only feature that attracts people. Because of elevation, people could also have a view to the waterfront and not necessarily easy access, which also commands a higher price than not. So average index basically measures that. Average basements is the average number of basements per houses in that census tract. Average water distance, this is an important one, of course, given the context, as I said, which is the average distance to the nearest waterfront from the houses in the census tract. So whether it's a lake or the inward bay, with whatever part of that context you're looking at, but the average distance to the nearest waterfront. Then there is average square footage of living area, which is a very obvious structural feature that we would want to add, and an average age of your structure. So whether your housing unit is older or it is newer. So these are the independent variables we'll use, and these are the dependent option variables that we have. So as we see for the distribution, it's always very helpful to see the distribution of your dependent variable. Especially, it is always helpful to also see it for your independent variables. But for a dependent variable, it is very important because in OLS or in normal normal regression frameworks, the assumption is that the dependent variable is normally distributed. That is the underlying assumption. So if your dependent variable is in fact not normally distributed, your model is going to be a misspecification and it is going to have problems. So for example, our dependent variable is definitely a skewed variable because our average price is 500,000 in like around 500,000 in a lot of places, but it also goes to up to 3 million in some census tracts. So this is a very skewed data set. And if we were to just use average house prices as the dependent variable, it would give us problems. So there are many ways in which to handle this. The easiest one is to just transform your variable. Of course, you can use like spline models, or you can use some forms of additive models where they do not have this assumption of normality for dependent variables. But the easiest way is to just log transform your dependent variable. This is very, very commonly done in hedonic house price modeling. And so we're just going to do that. And this is an interesting aspect to know also about regression, is that the assumption of normality is very important. So once you transform the average house prices, it sort of is normal. I won't say this is still an ideal normal variable, but we can still work with this. At this stage, if you were to do this for a publication or some research, you would go ahead and want to delete some outliers or want to inspect other transformations like box and Cox or some other ones that are available. So we will be using the log transformed average price, which is the ln average price in our table. So great. At this stage, I am going to do this live. So you can either follow along what I'm doing, because I'll be talking through each and every part of the interface and trying to tell you all the different options that are available. Or you can also look at these screenshots if they're handy, and if you lose track of where I am at, they will still come in handy for you to follow along. So if you're still in full screen mode and you want to follow along, just minimize the the window on one side of your screen, and this is where we will open the MGWR software that you would have downloaded. At any point, if people are following along and they need more time, I'm happy to pause for 1 or 2 minutes or even more if people want to follow along. And you should have two things here. You should have the downloaded software and the downloaded data set from this link on the page. Okay, so this is somewhat, sorry. Is that a question?
No, we don't have any questions yet, Mehak, but maybe give people a second to make sure everyone's ready to roll here, I think. But yeah, no questions yet in the question sections.
Sure, yeah, I'm happy to wait for about a minute or so. If people need more time, please feel free to let us know.
Well, we can give you a break too. You've been talking for quite a while.
Thank you. Great. I think we can move along. I don't see any chat or, okay, Diana said that she would Unmute her. Okay. So if there are no questions, I can start doing the actual example stuff now. So I'm just going to go ahead and open the software that you would have downloaded or I have on my desktop. So this is what the interface should look like. I'm just going to resize it so it looks good. If there are any size problems that you're not being able to see it or anything, please let me know. I'm happy to adjust that also. I can hear someone unmute the session. No. Okay. Great. So this is what your interface should look like at this point. It's very simple. It's very, very clean. And I will talk through each and every. It may look a little intimidating to begin with because of all these options and what all they do. But because we've had a good conceptual building into this, I think you will all be able to follow along of what is happening. So to just input your data from wherever your file is located, the first step is under the data files to press these 3-dot button. So this is the button that I would, so when I go on that, it becomes blue and it's highlighted. So it's basically a link to getting your data set from wherever it is on your system. So I would just click that, and where that would take me would be in my entire system. So it's going into Windows C right now. My data set is in downloads. So this is where my data set is. So I would just navigate to downloads and I would select my CSV of wherever it is. So it just comes up here. These are all the options that you can also you can have in here. And then I'll just click open. Again, I am really happy to stop at any point, so please let me know. Otherwise, I'll keep going. But if there are any questions, I'm extremely okay to stop. We will have time for other things. So now again, I would encourage people to not copy this this path to that file, because this is the path to my local system, and this is where I am uploading the file from. So this will definitely be different for you. So the best way to get data set from your own system is to click on these 3 dots and navigate to the folder where your file is and click that and get it in. So a very cool part about this interface is that the moment you do that in an accepted file format like a CSV, it populates your entire variable list with all the columns that are there in your data set. So we talked about all the independent and dependent columns and the location, like latitude, longitude, those columns, everything is in here. So this is the first, sanity check that you would want to do when you're putting in your own data set to see whether your data, all the columns are showing up or not, and whether the format is correct or not. Because there are some times that if it's a comma separated file and you are looking at some, a weird format, that the columns will not be detected and the variable list will not be populated. Great. So now one by one, we'll start putting in the variables that are going to be used in our model. We've discussed about that too, but I'll be going through that again. So it really drives home of what we are trying to do here. In the location variables, so because it's a local regression, we need a location variable for location, like a point for each of the data points. This is an ID variable, which is optional. This should be, if you have an index variable, which has a different value for each and every row, this is what you would input here. If you don't have one, then the software will go ahead and generate one for you. The IND variable in our data set is the index variable. So I'm going to input that as the ID variable. So how you would input a variable into any of these columns is that you would select it. So when you select any variable, it would turn blue with a blue box around it. And wherever you want to input it, you would click that arrow, the left arrow. So for ID, if I click the left arrow, that goes in here. Again, if I want to remove it, that is the right arrow. If I want to put it in, that would be the left arrow. So if I was to if I was like, oh, this is not the variable I wanted, I would just click here and it would depopulate it. So again, if you select it and use the left arrow, that is where it will populate. And this will then come in handy for all the other things, all the other input variables that we are using. Now in our data set, we have latitude and longitude. We see latitude and I'm not seeing it. Yeah, longitude. So we have spherical coordinates and we don't have projected coordinates. Now it's possible that in your data set, when you use it in your research, you have projected coordinates. So that is when you would use this. But I'm going to go ahead and change this to spherical because we have latitude and longitude in our spatial data. So once you click to spherical, your column names change to lon and lat. So it's easy to identify where to input which variable. Again, if it was projected, this would be X and Y. If I click to spherical, it would be lon and lat. So for the longitude, I will go ahead and select the longitude variable and populate it here. And I would go ahead and select the latitude variable and input it here. If people are being able to follow along, I would be happy to move on. Or if people have doubts, I'm also happy to stop. But one thing I did not mention was that I'm using a Windows system. So the GUI, the interface may look a little different from yours if you're using a Mac. It is essentially the same thing. It's just that some of the buttons might be a little different. Like, of course, the cross I know is on the other side or something like that. So just don't be thrown off from what you're looking at here and what you have on your system. Okay, so let's get into the model. We have two options here. Either we can run the GWR model or the MGWR model. We'll be running the MGWR because that is the point of the workshop, to introduce to you the process scales and the newest version. But you might want to, for your own research, want to compare results from GWR, and you might want to then run this. But we'll keep this selected. Now, spatial kernel, this is where the bandwidth parameter again comes into play, and this is where the conceptual understanding we had about the bandwidth will come in handy. Again, on the page, if you can see, this is the diagram, and I'm going to go through that again. So there are two options for the spatial kernel that we will be using for the weighting. Remember, where we want to calibrate a model at every location, which is the X, and we are weighting the data sets from around there to calibrate that model. So there are two options to select what kind of a kernel you want. One is an adaptive, and the other is a fixed. Now, how they are different is that if you choose adaptive, that kernel adapts to whether you have a dense points around that X or if you have sparser points around that X. Now, if you are using a data set like this, as you see in this figure, there are many points in this region, but there are not many points in this region. So when the model is being calibrated at this X, the kernel is tighter because it gets as many points it needs here immediately as it needs. But in this, because the points are farther away, the kernel adjusts its size to get as many points as it wants for the calibration. In the fixed, that does not happen. The kernel size remains fixed. So even if you want to do the calibration at this point, it will get a lot more points than it possibly or probably needs. And in this, it will get just about enough. But the weighting kernel size will not change. Now, I know you must be wondering, why would I ever want to use a fixed, weighting kernel? That is for data sets where you have an evenly spread out data set. I know that's not usually the case in point data sets or in administrative boundary centroid data sets. But if you have a grid data set, for example, and if you're looking at a centroid for each grid, then it's a very regularly spaced, evenly spaced data set, and then you might want to use the fixed. But in our case, because we are using census tracts, and of course it is not evenly distributed, it's not evenly spread out, we are going to be using an adaptive kernel. What bi-square tells us, there's only one option, it's bi-square for adaptive. It is just the function, the diminishing function that is used. So it's just the how and when that diminishing is going to happen as you move further away from the calibration point. Again, in bandwidth searching, if you already have some literature, through some literature, you have an idea of what scales to expect certain processes in, you can define your bandwidth by an interval search, but usually you would want the system to come up with an optimized bandwidth for each of your processes using the golden section criterion. So we are going to use that in our thing. So, okay, the left part of that of our thing is sorted. Now we have all the variable lists and we want to put it into the regression variables. So we want to define what our y variable or our dependent variable is going to be. And we want to populate this entire list with all our local independent variables. So as we discussed, because of the log transformation, we are going to use the natural log of the average price. So I will again click on that. And for the y, I would input it using the right arrow on this side. So here now we have the natural log of the average price variable. For all your independent variables, you can either select them one by one and use this arrow, or you can select multiple variables using a control key in Windows or your command key in a Mac system. So again, this screenshot will come in handy. All these are the ones that we are going to use. So I'm going to select them using a control command and input them all at once. So we are definitely using average age. We are using average water distance. We are using average square footage of living area, average basement. Make sure to not select average price because that would just give you 100% fit, because that would just be modeling your dependent variable with your dependent variable. So that would really lead to a wrong model. Average index, average unemployment, and average tech. These are all the variables that we are using. They are a total of 7, and including the constant, a total of 8. So all these are selected blue. I would just do this, and this populates all my independent variables in this box. If everyone is following along, and if they have any questions, please feel free to unmute yourself. This is a good place where you might want to just interject me and ask me any questions, and I'm happy to answer. But your screen should look like this. Okay, there is something. Does the order of variables in the list matter? That's a great question, and no, it does not matter at all. So basically, yeah, you can have your variables look in any order apart from this, and that would still be totally fine. How we would be interpreting all this, which is a very important point, is how we would be interpreting this is that holding all other variables constant, what is that, how much is that process affecting? So I will get to that again, but these are all marginal processes. So it is not going to matter whether you put that first or after. And it's an additive model. So again, it will not matter. But thank you. That was a very good question. Great. Now, if your thing looks like this, we are pretty much good to go, but I am going to talk about a few more things that could be helpful to you if you're using this for your own research. So the model type, again, this is a Gaussian model. Right now in MGWR, we do not support a Poisson or a linear binomial model where your y variable is supposed to be continuous, is what we expect right now. But you could have, like a disease count data set as a dependent variable, which would be a Poisson model. But we are working on it, but that's not available right now, unfortunately. So right now we have only one option, but there will be others available later. The optimization criterion, this is the criterion which is used, statistical criterion that is used to, the statistical criterion that is used to see the bandwidth, to find the optimal bandwidth for each process. So AICC is the default one that we usually use. It's the most popular one also. That is why we use it. But if you have any other reason or any any other background reason to use it, you can select from the cross-validation or BIC or AIC. Or you can also do a cross, I don't know, exploration of how these are different. But we'll use AICC for now. Then there's this advanced button where you can have other options available in MGWR. Since that is a lot to go through right now, I'm still going to show you what all is available. And then this is a good place where you might want to have follow-up questions later if you think there is anything relevant there for your research. So in the advanced option, there are many things happening. So I'm going to go one by one. Variable standardization. So what this basically does is that it standardizes your variables to have a standard deviation of 1 and mean of 0. All the variables will be standardized. Why we would want to do that, especially for MGWR, is that we want to be able to compare the bandwidths amongst each other. So suppose I get a bandwidth of 45 of average age out of 350, and we get a bandwidth for water distance as 200. I can compare them, right? That 45 is definitely lesser than 200, and so average age is a more local process than is, water distance. If we do not standardize the variables, then those processes and their units will come into play for those bandwidths, and we will not be able to cross-compare the bandwidths across the processes. So for MGWR, you have to make sure, and that is why it is on by default, but you have to make sure for MGWR, the variable standardization is on. For GWR, it does not matter. Now, initialization. So in MGWR, how it works is that the bandwidths are first initialized with their GWR estimates. So if in the background, it runs a GWR first, it finds one bandwidth parameter for all the variables, and then it starts doing the algorithm to find one for each of the processes. You can also choose OLS, or you can choose GWR. We go with GWR because we feel that we have found through experiments that is faster. But if you have any reason, you can change that too. Now, there are tests for spatial variability, and there are local collinearity diagnostics that you definitely want to do if you are using this research for publication. What your test for spatial variability will tell you is that your betas, your processes that we are constantly saying are heterogeneous, and we are saying that they vary with space, are they significantly varying with space, or is it just noise? This test would tell you that. So it's very, very handy to actually use this test and only then interpret your variables. This test is because it's a Monte Carlo algorithm. It takes a long time to run. So unfortunately, we will not be using that also today. Again, this would have been something in the 2-hour workshop, but definitely cannot fit in this. In the 4-hour workshop, but cannot fit in this. But definitely something you want to do when you're doing it. But also note that this takes a long time to run. Same as with the local collinearity diagnostics. So there is, if you've heard of this before, there are multi-collinearity issues that often come in regression modeling, where basically you are getting the same information from 2 separate variables. So there is an overlap of the information that you're getting, and that can sometimes lead to spurious results, or even a change in sign of your processes. So that has a different effect when it's a local regression model. So those tests definitely need to be also done for your beta parameters. I will just skip these two, which is measure of scope of change and convergence threshold. These are basically the algorithm parameters that define the backfitting algorithm that MGWR uses. It is best to leave it to that. Just as an FYI, if you want to run a quick test and don't want to really use those for publication, you can reduce your convergence threshold to 3, and that would be much faster. But if you want to publish your results, we recommend using the 5 that is default. Again, there are the papers that are in the on the website here that I have written. You can follow those papers for more on these inference and different tests that are here. Something that we recently added is confidence interval for bandwidths, and that will tell you how wide is that range for your bandwidth parameter. And today we are only discussing that one bandwidth parameter, but this is a very handy thing also to do if you're using this tool for for your research. Again, this also uses a bootstrapping method, so it also takes a longer duration than not. So all these advanced criteria are something that you will definitely want in your want to change and play around with in your research. But for today, we are just going to use the default ones to see how can we interpret those parameters. So this is all set. Now, the last thing we need to input is the location where we would want our files to be stored. So there are two outputs that come out of the software model running. One is a summary file, which is basically a text document that gives you a summary of all the model fitting criterion and whatever you chose and the answers. I mean, sorry, not answers, but the parameters that came out of it. And then there is a CSV file, which will give you the beta parameter for each process for each location. This estimate is what you would be mapping, and this is the one that you would just be looking at and interpreting the results from. I will be going through both of these results and what they mean and what they show. Here, so that is why you need to define, just to define where you want that, just click again on the 3-dot button. And that will again take you to where you would want to store these. I'm just going to store them again in my downloads folder. I'm going to leave the default name as MGWR session. So what it would do is that it would store one file as MGWR session summary and the other as MGWR session results. So if I just choose this and I put save, you see how this got populated with the path to my directory. So it's MGWR session summary.txt, which is a text file, and MGWR session results.csv, which is the CSV file. Now, once all this is set and you have input all the criterion like I have, we'll just press run. Now, at this stage, it's going to take about 1.5 minutes or so. I mean, that is the amount it takes on my computer. It might vary with your system. It might be lesser if you have more cores, and it will be smaller. It will be like more lengthy if you have lesser cores. But so this is interesting to see that while the model is running, you can see behind the scenes how the calibration is happening for the model. The bandwidths for each process are coming out. So this is also where I think, Amy, your question would be addressed. So how I will be reading these bandwidths is according to the way my variables are input. If your variables were jumbled, then your bandwidths will also be jumbled, like accordingly. So I just have to read. So 43 is for the intercept right now, 45 is for average age, and I mean, it's still calibrating, but that is how I would read it. So if your variables are different, then you would read these iterations differently. But again, in the summary file, we'll see that it falls back into place. So
Mehak,
yes.
Can I jump in for a quick second here? So while this is running for a second, can you just give us one step again? Would this look different if we ran it for GWR? And then does that reinforce the difference between GWR and MGWR? Just so we get that big picture again as we go into the interpretation section.
Sure. That's a very good point. Thank you, Peter. So yeah, if you were to click this, oh, sorry. Oh no, it will have to finish running for me to do that, but I will still go ahead and do that once it finishes. I think it's almost done.
Sure, but even just sort of conceptually, the big highlight difference here.
Yes, actually, let me just do that. So yeah, that's a very good point, because if you were to click GWR instead of MGWR, I think the biggest difference here would be not even here. Yeah, okay. So the biggest difference would be in the advanced section, because we talked about, when I said about the score of change and the thresholds that we are using, which is e to the power minus 10 or sorry, 1 to the power minus 10 or 1 to the power minus 3. That does not hold true for GWR. So you will have limited options in your advanced options. So you will still have the variable standardization. I don't know why. Okay. You'll still have variable standardization. This you can switch off. You'll still have the test and the diagnostics, and you will still have the bandwidth confidence. And if I was to run that, I'm just quickly going to do that, but you don't have to. And I'm going to change. So this is all default. And I'm going to change this to desktop so it doesn't overwrite my results. And this is GWR, Spherical, everything is the same. And if I run it, of course, it took like, so MGWR, as you saw, took 1 minute and about 40 seconds. And this took microseconds, nanoseconds, I don't know, to finish. So this you would see then in the results, we can walk later, but it did not do the bandwidth figuring out that we were seeing the previous one do. And that it was doing because it was giving us a bandwidth parameter for each process. Here you will get a single bandwidth parameter estimate for your for all your processes, basically. So again, yeah, that was a very good point, Peter. Thank you for pointing it out. But yeah, if you would want to compare your GWR to MGWR results, this is handy. But otherwise, MGWR is what you would want to look into, even if you're using exploratory research. So if I'm not mistaken, so this is the summary file that came out of running this. So once I ran this with the MGWR, it's saved, and I had saved this in my downloads, remember before. So we will see here, it is now, there are two files. One was the example data set, was already the one that we used, that was our data set. And the ones that the software has given us are the MGWR session summary and the MGWR session results. As you see, this is the text file with all the summary details, and this is the CSV file. Now I'm going to walk through both of them and like interpret the outputs. So, I mean, either we can just go through I could just walk through the, the summary as I see it here, but I will just go back to the page that I have constructed because I have highlighted things so that we can talk about them in detail. At this stage, I just want to make sure that whoever was following along as I do, that they were also able to run the model, and if in case they had any errors or any other reason why it did not work, I'm happy to pause for a second and chat about that. If not, I can just move on.
I don't see any immediate questions, Mehak, but anyone can raise their hand or put a question at any time. I'm happy to flag them whenever they come in.
Perfect. Thank you so much, Peter. Great. So I'm just going to minimize all this and go back to our results now. So this is where the fun begins, at least for me. So right now we want to see what the results and what do they mean. In the MGWR summary, so the MGWR software also runs a global regression, and it gives you the parameter estimates and also the R squared, which is the explained variance of your dependent variable in MGWR also. So this is the global model result. R squared, how this is interpreted is that you just multiply it into 100. So the model is explaining 89% of the variance, almost 90% of the variance in the dependent variable. That is an incredible fit. For most social science models, we do not see, I think the maximum I've seen it is like 45 or 50% for a global regression model. Remember that they do not consider spatial heterogeneity at all in processes. So the R squared is lower in global models than in local regression models. But this is a good fit. Also, this goes on to say that this is also an average data set that we were using, and that has something to do with unusually higher explained variances. But so you see the R squared and the adjusted R squared. The adjusted R squared is basically just also taking into consideration the number of variables that you use. So if I had used 20 variables, my adjusted R squared would be lesser because it means that I'm using too much information to not get as much out. So it penalizes if you use a lot of variables. But R square is the one that usually is talked about in research when trying to explain model fit. And we see that all the variables are very significant because the p-value is 0 for all of them. Now, MGWR model results. In the summary file, you will also find the MGWR results, just like these. And the R square for MGWR comes out to be 98%, as we see. Again, when I ran this model with the 20,000 data points and the same exact model, I got an R square for a global model of about 80%, 78%, and the MGWR was 92%. these R-squares are inflated because we used aggregated data set. And that is almost always the case because the variance gets lesser and the model fit is always higher. But that's great. So we already see the difference between doing an OLS model versus an MGWR model, because if we take into consideration spatial heterogeneity, we see our R-square jump up, which is also one of the things that we can say that there was spatial heterogeneity in our processes. Now, this is an interesting part. Again, we've been talking a lot about process scale, and this is where it really comes to. So our census tracts, so the number of census tracts in our study area were 357. So you always, when you use adaptive spatial kernel, you always compare your bandwidth to your total number of data points. So your total number of data points here are 357. That is your entire study area. So now for the average age, for example, you get a bandwidth of 45. So 45 out of 357, that is local, I would say. You're only using 45 nearest neighbors to calibrate your local model, which means that that much information is enough to give you a calibration, a significant calibration of your model. For average basement, we see that the bandwidth is 103, so which is about 1/3. So that could be identified as regional, I would say, right? Because you're using 1/3 of the area and calibrating the local models. Again, average square footage and average water distance are very local. Average unemployment, like you see, is 277, which is almost global. Like you're using a major part of your entire study area. Just to visualize what that, yes.
A quick question on these. So
yes.
with the bandwidths that you're showing there, are
yes.
those to be interpreted as averages for any point, like across all the points in the region, not localized to a specific point, correct?
Yes, absolutely correct. Yes, that is a very good point. So these bandwidths are the same for every location. They differ for each process, but they're the same for every location. So for example, when the bandwidth is 43 and the calibration point is assumed to be this center, the darkest red, and then it would take this area. When this calibration point moves here, for example, there would be another exactly the same amount of area that we would use, that is 43 neighboring census tracts. That is exactly true. And then for the bandwidth of 180, you see the area starts to expand. So now you see why I call this local. This is kind of regional. We are using a lot of the census tracts around to weigh our data. And 354, because our entire data set is 357, it is completely global. So we are using almost all of the data set to calibrate a model. So here we see how, this is an important aspect of any regression model that we would want to see. We would want to understand if the processes affecting our data are local, or are they, operating at a regional scale.
Mehak, we have
yes.
a question.
Yes.
Sorry, we have a question from one of the attendees. Jochen is asking, or he's noting that his bandwidth values were a bit different from yours. So in his running for age, for instance, he had a bandwidth of 356. So if you could comment on that potentially.
Age, is that correct? Sorry, was that for average
yes,
age?
for age. Yeah, age. Mm-hmm.
That is interesting. I just want to make sure if you use the advanced initialization to be GWR or OLS. Sometimes, so again, the bandwidths are, the result of an optimization criteria. So if I was to use the estimates from GWR to OLS, that would definitely vary my bandwidths. The other reason that could be possible is that the confidence intervals are too large. Is he asking some other question as well, or?
Jochen is just saying that he used the same advanced parameters, so maybe there was some crisscross somewhere in there.
Yeah, I think that's interesting, because so if your parameter was changing for some other one, like for example, average, if your average unemployment was 356 instead of 277, I would feel like that's possible completely, because essentially the interpretation is the same. But for average age, because I'm getting a very local one, that's very interesting. I don't at the top of my head know exactly why that would be happening. Either I don't know if one of the variables was different or missing, or
it's possible. Tiffany said she has a similar experience where she also got different values, but perhaps we can circle back to this and try to sort it out in a minute here. The one other thing I would make a mention is that Samaya Dodge did get the same bandwidth parameters, but she also wanted to ask a quick question about the units for the bandwidth. She's just confirming that the units for the bandwidth are the number of points or census tracks and troids, not a distance in this case. They're the count of the points, correct?
That is absolutely correct. So exactly true. And if you were to use adaptive, you would get nearest neighbors. If you use fixed here, that would give you distance. So yes, because we use adaptive, and that is why we are using, and the points are the centroids of census tracts. So essentially in the interpretation, we would say 43 census tracts or 180 census tracts. But it's very interesting that people got different bandwidths. Again, if your bandwidths are differing by 5 or 10 or something, I would not worry. But because the average age is so local and someone is getting like in 200s or 300s, I would really want to circle back to that. So that's a very interesting observation, and we can chat more about that in a bit. So that is, I think, but that's
Thanks,
yeah, that's also very interesting, because I would again point out that if we were to switch on the confidence intervals, that would give us a better picture. Maybe the average age is just like, just overall. Oh, actually, I know what is happening. Sorry, I'm just thinking aloud. But okay, I'll get back to it when we get to the interpretation of the parameter estimates, and I think that is where we will get to the bottom of why this is happening. Great. Thank you for all the questions. I really appreciate, and this gives me confidence that people are following along and getting something out of this. Great.
Yeah, and I think we're caught up on questions at the moment, Mehak, so if you want to press forward, you're good to go.
Yes, yeah. Thank you, Peter. Yes, that's helpful. Great. So for the parameter estimates in the summary summary text file, we will get, because there is a beta estimate for each process at each location. We only give a table of the mean, standard deviation, minimum, maximum, and median. This is just a quick and dirty way to see your parameter estimates, but ideally you want to map them out, and that is what we are doing next. So in your results CSV file that you would have as the output, as one of the outputs in the software, you would see that you have all these new columns added to your CSV. I will start from 5. That is all the columns starting with beta are the ones that have the parameter estimates. So beta underscore average age would be parameter estimates for average age. Beta underscore average basement would be for that process. So those are all the betas that you would get. All columns starting with SE would have standard errors for those processes at each location. Every column starting with T would have the T values, which defines the significance of the parameter estimates. This parameter is extremely important because we only want to look at the significant parameter estimates. Many times it happens is that we get all the parameter estimates, that is one value for each of our 357 points, but none of them would be significant. That is just essentially noise, that it could have resulted from a random model also. So we really do want to check that what is the probability that this is a significant parameter versus not, and that is calculated by the T value. The P value essentially uses the t-test and converts that into the P value. And then this is just some of the weights for each covariate that is being used at each point. So these are very handy ones. The ones that we usually use to map, as I will show next, are the beta columns and the T columns. Now, there are other very important columns that are also in the output file. One is the OLS residue, which often if you map, you will understand what is the error from the model at each point in your data set. So for each census tract, what is the residual from a global model? And then you can plot the MGWR residual, that what is the error for each census tract from your MGWR model. And on comparing these two, you often get a very interesting idea of how your model fit is different between the two models. So unfortunately, again, we won't get to the residual part of it, but you will observe in many papers that you read either from GWR or MGWR that these are always compared, and they get to the bottom of why spatial and local regression is gives us more information than global models do. Because also we are only at 35 minutes of the end time, I'm going to jump straight into the mapping. Again, sorry. So yeah, this is important because, as I said, that we only want to use the parameter estimates that are significant. So we want to use the t values. Now, there are, in the summary file, you will find an adjusted t value, which is our critical t value. So for every process, it's different. So for average age, it is 2.9, and for average unemployment, it's only 2.1. You want to mask off the column, mask off the rows that are not the critical t value, and you only want to plot those betas. So I will, I'm going to show you how to do it in Python, but unfortunately, if you want to do it in some other software, you can still do that very easily, but it is just a matter of choice of how you want to do it. So the last portion here is about mapping parameter coefficients. Now I was a little ambitious when I thought that I could go along make everyone follow along the Python code. Probably that is not going to happen, but if you are familiar and if you really want to run the entire code, you want to follow this link, and that will lead you to a Google Colaboratory notebook that has the entire code that you can run from your system, and it will not give you any errors. Even if you don't have Python, if you don't have anything, you can still run the whole code, and it will do exactly what I'm going to explain. So feel free to do that, and feel free to contribute to this. It'll be interesting to see if people have other ideas. I'm not a coder by any means, so I only do things to make things happen, but I'm happy to collaborate if anyone else has any ideas. Again, so the CSV that you have from the results can easily be joined in any mapping software like ArcMap or QGIS, and the results can be plotted essentially. I'm going to do that through Python, but completely easy to do it in ArcMap or QGIS. So don't get put off by, oh, I don't know Python, how am I going to map these results? So, but the most important part that I really want to get to is that you want to mask off your insignificant values and not use them. So in the code, these are the columns that came out of the results file. These are my critical t values. And what this code essentially does is that it removes all the values that are not critical, not in the critical t value range. So you really want to do that. And that is how I'm defining these new columns that are then the only significant beta parameter estimates. So all the BT columns are the ones that we are going to map. In the code, you will also see this block if you're following along. This basically just joins the results to the shapefile, which is the step that you would need to do irrespective of what medium you're using, because the resulting file will only give you the latitude, longitude, and all the result columns. It will not necessarily give you your shapefiles. So you need to just join the centroid back to your shapefile that you will have, and that can be easily done in ArcMap also. So this is just essentially what that is doing. Once you have that, you can map your parameter estimates. So instead of having just one value of beta for each process across the entire study area, now you have 357 values that you're going to see. Now, I'm again going to get to the point of why you want to map only significant parameter estimates, because you will see what happens if you don't. This is a map of all the parameter estimates for average age. So how this will be interpreted, if I was given this map and I was to write a story about it, I would say, oh yeah, like, these are basically the older neighborhoods like Ballard, if you know the context. These are older neighborhoods, and as the house age goes up, house values also go up, because you see this is positive here. In these areas, all that are dark blue. So I'll start making, correlations that, oh, near the airport, if there are people prefer newer housing. So as age of a housing goes up, prices tend to decrease. These are just mapping all the values. But in fact, if you map only the significant values, this is the map that you get. So as you see, all the blue ones have disappeared, right? So once all the blue ones have disappeared, this is telling us nothing. So all these blank spots are telling us nothing. There is no information that we can get from there. So it is completely wrong if we try to interpret that in any way. So you only want to interpret this map, which is now we are using the BT age from the code, which is the significant parameter estimates. And now I'm just guessing this, but I'm getting back to that bandwidth, for average age, because there are so many insignificant values. I am not surprised that the bandwidth could be global also for this one, because if you see this one now, how the bandwidth comes into play is that beta parameters for this are very different from betas for this, and that changes rapidly over time. So over distance. So 43 or 45 makes sense if you see like all these parameter estimates. But here it's basically a very similar trend that you see. Wherever the parameter estimates are significant, you basically see this like a very similar, thing. So I don't know if that is what it is, but I'm guessing that could be one of the reasons why the bandwidths vary so much. But I would still want to get to the bottom of that, and I will follow up on that later too. But
a quick related question there, Mehak.
Mm-hmm.
So when you do the MGWR,
yes.
Should you expect to get the same single solution every time, or would you expect there to be some variance in the estimates of these parameters run to run if you were to run it again and again?
That's a very good question. Thank you, Peter. You would definitely expect differences. That is, I think it goes on to say about there's no single answer for anything, of course, and it's all on interpretation. But the other point of why that happens is because it is a statistical model, and with every run, ultimately it is using an optimization algorithm behind the scenes. So you will always get slightly different or maybe like different results, but the hope is, or the entire bottom line is, that the significant results would lead to similar interpretation, is what I can say. So even if you ran the exact same model, maybe the parameter map looks slightly different, but the interpretation would be what I am getting to here. And that goes on to say why these models are best used as exploratory tools, and how these parameters are interpreted are like suggestive. They are definitely not conclusive. Like you just cannot say that this is exactly the amount of housing price that would increase or decrease if your house was 1 year older. This is suggestive, and this, of course, we are doing it again. The other part of this is that we are doing it at a census tract level. So we are only talking about averages here, which is also a whole new level of exploration. And this is definitely not in any way an answer to any problem.
Right, and I only bring it up because, unlike traditional like OLS regression, where you actually compute mathematically the parameter, right?
Yes.
And there's sort of one parameter. This is estimated by an algorithm, right? So there's
yes.
a little bit different procedure. So you'd expect some shift, some variance between the estimates of the bandwidth, although you would hope it would be relatively small, right? So I just bring it up for that reason. So.
Yes, that is very true. Thank you, Peter. Yeah, that's absolutely true. And that is why I feel like all these confidence intervals and all diagnostic tests are very important, because I think when you start doing all of those, the interpretation could be, you would essentially lead to the same interpretation answer, not the actual answer, maybe. But I hope this really drives home the point of the significant parameter estimates versus not, because we see that in so many papers on GWR and MGWR, and it is just sad because this is not what we want to interpret at all. I'm just going to run through all the maps, but then I'm going to focus on one quickly to tell you how we would interpret these exact numbers here. But so yeah, this is the map of a nearest waterfront distance. So it is blue because what this means is that as the distance to your nearest waterfront of an average house increases, the house prices go down. of course, because you're not close to the water anymore. So this makes sense. But now we begin to see how important it is to use local regression versus global regression. Because in global regression, it would have told me that that one parameter is true for all these census tracts. But now we see how radically different it can be and how insignificant it can be in some areas. So here it's totally believable there are no water bodies, or if there are, then they are not significantly developed that people actually attribute any value to the distance to that waterfront. But if you see in areas near Lake Washington or near the Inward Bay area where there is a beach, Alki Beach Park and Discovery Park, there people actually attribute value to being close to the water body. So you see darker blues there versus lighter blues or just insignificant values in the rest of the places. So this is essentially the core and the crux of why you would want to use a local regression technique rather than global, because there's just so much more information you get out of this. And the other thing is that how you would want to interpret these results is that holding all other parameters constant, the price of water, the price of the house changes by these values as the distance increases, because we have included all the other processes also. But we are assuming they are all constant, and then how this one variable affects the price is what we are interpreting by this one map. So it needs to be understood that we are always talking about marginal effects of processes holding all other processes constant. Similarly, we see all these maps for different things. So for square footage of living area, as increase in square footage of living area would obviously increase house prices. So all the values are red. It is just the marginal value of space is more in some areas versus other. Sure, that is something that you then start to interpret and starting to do that. Sorry, Peter, I again. Yeah. I saw the question.
No, we got it. Oh, you did? Yeah. Okay, go ahead then. Sorry.
Great, thank you. Yeah, no, that's good. I was just going to say that. Yes, so to clarify, it's omitting rows from the map where the t-value is outside the significant range. Exactly true. So that is exactly true. When we look at these are the critical values. So how t critical values would be, this is 2.92 so for the interpret. So for the intercept, we would exclude all the t column, t rows where the value is, we would exclude all the rows where the value is between 2.92 and minus 2.92. So we would take into consideration all the values above 2.92 and lower than minus 2.92. And that we would do for all of them. And that is what this is doing. So if the t column is greater than equal to the t critical, then populate my row. And if the t column is less than equal to minus t critical, then populate my row. Otherwise, don't populate my row. So this is what it is doing for each of the columns. So that is true for all of these. So for water distance, you would want to omit values that are between 2.67 and minus 2.67, but you would want to include above 2.67 and below minus 2.67. So this is essentially, yes. So that's a very good doubt, and I hope that clarifies that. And that is why you would see in the places that you see, like in square footage of living area, you see a parameter estimate, a significant parameter estimate for each of the census tract, because that parameter estimate is just significant for all of the study area. Whereas waterfront distance, and intuitively so, is not. So you see a different one, and you see these patches where it is insignificant. So then we have a map for every, of course, every process, and for every census tract, we have a beta value. So I'll just go ahead and, I mean, we can talk about each and every map, but like that's not the point of this workshop. I just want to drive home how you would then begin to interpret exactly one map with the values that you see. So it becomes very important to A, consider the model that you used, and B, consider the scale at which you employed that model. So I'm going to take into consideration the water distance parameter estimates. Again, so this is the map as we saw before. So what do these numbers actually mean? Like how can I actually talk about these numbers meaningfully, and what do they mean? So because we used a log linear model, remember we log transformed our y variable and we used our x variables as is. So that is called a log linear model. So for a log linear model, the interpretation would be as follows. 1 unit increase in your x, whatever crosses, would change the house price by this formula percentage. So you have to like so because you transformed your y to a log, to a natural log, you also have to transform your betas back to make it meaningful in terms of the unit, right? So now to make it meaningful, we just have to employ this formula for each of these numbers to talk about them. I mean, you don't need to do it for each of these numbers. You can just do it for the maximum and the minimum or whatever is it that you are trying to talk about. So in this case, I want to do it for the maximum. I want to see, okay, what does this actually mean if a house here was to increase, if the houses in the census tract were to move by 1 unit of distance from the nearest waterfront, how much would that house price value decrease? So when you employ this formula, you get minus 45. So then you would say that from the map above, with every unit increase in average distance of houses to the waterfront, near Bill Gates' house and University of Washington, holding all other variables constant, of course, the house price would decrease by approximately 45%. So because we calculated here, that's 45% and it's minus, so it decreases. Now, this is a huge change. I mean, this is radically different from what we would be observing here and what our beta for our global model would be saying. So this is a good point to start comparing that. In our global model, the beta that we got was minus 0.21. If we convert that, that gives us minus 19%, say, for example. So what our global regression model would have been interpreted as was that if you increase the average distance from the waterfront of a house anywhere in the study area, your house price would decrease by 18%. That is not true, right? I mean, here it would possibly not increase, of course, holding all of the variables constant. But that's not true because here, of course, it would probably not even affect it because it doesn't matter if it changes or it doesn't change. But here it would actually change your house price value by 45%, which is a huge difference from 18%. But this is basically how you would get down to the numbers, and you have to transform them back and then like talk about that story. And again, this is all suggestive. So we cannot state it as, changing the waterfront distance for a house causes the price to change. No, this is all suggestive that this is what the model is telling us. And then ideally, if you're using, of course, a census tract or something, you would want to then go into more details of what could be happening and why is it. So if you're looking at a census tract map like this and you don't really know there is a water body here, then you would first start to look at the water body. Oh yeah, that makes sense. If there is a lake here, house prices would be more sensitive around the lake. Now, why is it around this lake and not this lake? Because there is also Lake Sammamish here. Why is it more sensitive here? So then you get into the context more and then you start probing more and you find more answers. So this is the first step as a suggestion to a story that you may uncover. This is definitely not the end of it. But so I did actually go into this map a little bit more and I realized that the development around Lake Washington is a lot more than Lake Sammamish. This one is a more of, a trail lake kind of a path, and this one has more paths where people can actually, run and like visit. There are parks around here. There is a lot and people's houses actually, some of them open into their backyard has a lake. So that's pretty neat. So that is why this lake is way more valued than even like, a lake 5 census tracts away, or 20 census tracts away. So yeah, this is all just to say that if you use MGWR or any local regression framework, there is a lot more information that you get. And because we are using spatial data and we are using context as a key element of our research, I really believe that we should do that. Even if you lead to the conclusion that, okay, OLS in my case is better, and for my data set, the global model performs just as well. Sure, that is a great conclusion to have. but this is a very good exploration that you do want to include if you are talking about spatial associations and spatial patterns and spatial processes. I know I have been hand-wavy with a lot of concepts that I should have covered or I could have covered, but just given the limitation of the time, this is the amount that I could get to. So I'm just going to go back to the main page at this point and open it up for questions or any doubts, or you know, I think we were planning to maybe have another workshop at some point in summer. If people have any suggestions of what else they would love to learn or love for it to cover, I'm happy for suggestions like that too. But thank you everyone for attending the workshop, and I hope it was of some value to you all.
Yeah, thanks, Mehak. So I'll just echo that and say the floor is open for questions. And I think Mehak's final point there is like super useful and super important to remember that like looking for causal relationships in the real world is very, very difficult. And regression is really a step on that path. And MGWR is really offering sort of a more nuanced way to look for those kind of relationships. So certainly it seems to be a useful tool, and hopefully you guys have some questions that we can follow up with. And give Mehak a chance to breathe while I talk for a second.
Thank you, Peter. I also want to mention that I want to get back to that bandwidth problem. And I think I'm going to do a little bit of experimentation on my end, and I will, I do have all your emails, so I will get back to this email chat and I'll see what I find. I do want to follow up on that, but thank you for following along and letting me know that there was an anomaly like that.
Yeah, and if anyone does have a question at this point, I suppose there's no reason to just not have you unmute yourself and ask the question as well.
Right, exactly.
We don't need to necessarily go through the question form since we're through the presentation. So yeah.
Perfect. Thank you. Yeah.
Hi, everyone. This is Diana. Thank you very much for doing this. I have one question. I was not following along with the software
Okay.
and doing this myself, but I know that with one of the things that we've done in the past, or I've done in the past with other types of things that do some local and global measures of association and things, is try to use some different programs like this and run them in a way that students can compare the results that they would get from programs like these with the ones that might be built in to the software that they might be otherwise using. For example, I think that ArcGIS Pro and other Esri software would also run some GWR, although I don't know off the top of my head whether it's also Multiscale GWR. Have you ever done that? And would you expect? I mean, one of the challenges with the Esri software is that there's often not a way to appreciate what some of the parameters, how they've been set, what some of the different settings are. So I'd be interested in your thoughts on that experience.
Thank you, Diana. That's a very, very good question and observation. I have not personally done that, but in our group, a senior researcher did that, and he found that, so yeah, it is true that GWR is available on ArcMap in ArcGIS, and it is also available in R as a package. And those have not been, we have, like, none of the people who actually came up with the software actually contributed to the development of those. So those have been constructed independently from the papers and publications that have come out of these of this group. So they do have variations. Even in the R package, Zichi, our senior researcher, found that there were differences. There were slightly different ways in which they were optimizing the algorithm. There were ways in which they were using, whether the default parameter is AICC or not, or all those kind of parameters vary. In an open source package with R, you can change those parameters to make them like you would find in the software. But you're right, in ArcMap, there is not a lot of options to do that because it's essentially a black box and you don't know what is going on behind the scenes. Using ArcMap, we have found different results from in our software for GWR. Because they don't have MGWR yet, I don't know if that would vary too. But it is true. And the maps come out to look different also. So maybe their significance levels or significance testing is also different. But yeah, you're right. That is, and it's actually a very interesting research prospect, you know, to compare how it pans out in different places. Yeah.
I was thinking about it not necessarily from the research perspective, although that's certainly relevant. Yes. It was actually, I was thinking about it from the perspective of a session that Peter did a few hours ago today on reproducibility and replicability in GIS science research, and what it means for research to be done and published in a way where, you know, there could be not just the differences from a statistical process being modeled, but just from the, you know, the choice of the application that was used, and how we would behoove us in a way to think through what are the ways we can try to include not just the name of the package that we used in a methods section of research that we aim to publish, but, you know, what are some of the key, how can we make sure that people's research would be suited to be able to provide the key variables, the key parameters that they would want to make sure that that the reviewers and that the eventual audience would know had been set. You know, yeah.
That's a very good point. Yeah, that is true. It does really come into play for reproducibility. That is very true. Yes.
Right.
And we saw even with the same software, we had different answers today. So we still need work on that to figure that out. Yeah.
Yeah, I can hop in on that just briefly. I mean, some of the stuff that the UCGIS and the AAG did at the workshop this summer, and for those who aren't aware of it, there was a workshop on reproducible solutions for this kind of research hosted by AAG and UCGIS jointly at University of Illinois this summer. And essentially there, some of the infrastructure to try to answer that question is being built, particularly around the idea, at least for work like this, of having computational notebooks, which is essentially what Mehak did here in building out the example, where the code that you use basically encodes the choices you make for analysis. And then by sharing that code and that data, you're at least sharing the analytical procedures you used in that particular run. Now, there may still be variations in that, as we saw today with the parameter estimates being slightly different because of the way the algorithms are working. But at least if we know the algorithms and we know things like the seeds they're set to randomize from, we have some sense of how those things were operating. I mean, there's a lot more issues than that, just the reproducibility, but at least from the computational aspect of it, that's at least a first step that I know is going on with work from UCGIS and also more broadly as well.
Great. That's, yeah, thanks for, yeah, that's exactly what I was thinking about, how to make sure that we cultivate the practice of documenting those computational processes in our methodologies.
We have a number of questions too.
Oh, great.
One of the probably the, I don't know, this one's a challenging one, but it's actually a very good question. Junghua is asking about, we use the word process here, but the analysis that was executed today and is often executed in these kind of things is using cross-sectional data. So how much can we really measure a process, which obviously has a temporal component, when we're just using cross-sectional data? And are there any plans to extend these kind of frameworks across space, I think is the other implication in the question here.
That is a very good question. Yes, I know we do sometimes use the word process loosely for cross-sectional data, but in this, I think in this example, we only wanted to point out how the explanation of a quote-unquote process is different if you use MGWR versus OLS, but it's absolutely correct because you would use the same assumptions is the key here, that okay, if you were to say that house prices value in 2016 were to be affected by the census tracts of this year, census tract data for this year, then you would keep the same assumptions the same, and then what is the difference in MGWR? But there have been, if you have time data for like different years or different every 5-year interval or every decade or so, there is an extension to MGWR that also incorporates the time weighting. So you can also take into consideration one time step ahead or before, and then that actually really starts getting to the process. It is hard to find data of that quality for each year, and then because you would at least need 3 time steps to make any meaningful interpretation from that extension. But that's a good point, and it does exist. If you Google MGTWR, that is the time aspect also in it. And how they do it is just that they include another weighting matrix for time as well as for space. So that is how they would do that. But that's a good point. Mm-hmm.
That gets tricky too from a data standpoint. Like if you think about the housing example here, you don't have observations of prices continuously at all points in time, right? Because houses only sell at certain times. So that makes it a little tricky as well. Another question that came in from Fang is about the t-tests. And basically, do you have a multiple testing issue with these t variables that you're getting? And what does the degrees of freedom for those tests vary location to location is the question.
Yes, that is a very good question. That is absolutely right. We do have a multiple testing issue, and that is why for GWR and for MGWR, there is a correction that is used. It is based on the Bonferroni correction, and that is employed behind the scenes to calculate the critical t-value, which is why you see that emphasizing on the critical t-value is very important, because the critical t-value is born out of the multiple testing issue. And there is a paper by De Silva and Stuart Fotheringham where it provides. I can put that up on the screen. Okay, this one.
And Mehak, do you just use Bonferroni for that, or do you guys look at SciDec as well and things like this? Since we're talking about super technical details that probably no one's interested in, why not follow up?
yeah, but no, that's a good point. Actually, I think this is the one mentioned in this one is based on the Bonferroni, and then they do the Bonferroni correction for the multiple testing. But I'm not sure if for MGWR currently we are also doing, or we have also explored other options. I'm not sure, like the false discovery rate or something, right? Yeah.
Yeah, and just for those in the audience, yeah, the Bonferroni correction is known to be a bit conservative at times. So there's a potential, not an issue there, but something to be aware of if you're using it as well. But you can look into the literature on that as well. So.
You're right. I think this paper provides a comparison between the different ones, and it says the one that they're using in GWR and MGWR is optimal, so to say, but not very as conservative as Bonferroni actually. But you're right. Yeah, that is, I think, what this paper is about. But that's a very good question. It is an issue.
Yeah, a bit of a broader conceptual question from Amy here. Is there a scale at which MGWR is equally or less effective than GWR? I'm not sure if it's a feature of scale, but it's actually an interesting way to think about it.
Yeah, it's interesting. I think, statistically, there are many times that we have found that GWR is actually is providing a better model fit than MGWR. And that is because of the thing that if the GWR constant bandwidth is more local than the ones in MGWR, then it is basically overfitting. So you might have a data set where you do MGWR and GWR, and you find a better R-square and a lower AICC for GWR than MGWR. That is because it is sometimes, I mean, most of the times, I don't know all the cases, but most of the times it is because it's overfitting and it has a more local bandwidth. Why we still propagate MGWR more is because that is a more realistic way to look at it. And in GWR, where a constant bandwidth is an assumption, in MGWR, we relax that assumption. So we actually let the process be global if that's what it is. And because of that, sometimes the model fit does get lesser but it still provides more information. So yeah, that's a good question, but it's tricky to. I think it's all based on interpretation and your context.
Mm-hmm. Yeah, it's tricky too because you could define effectiveness in a couple of different ways. But maybe that's exactly. That's a philosophical question.
That's very important point also. Yeah, I agree. Yes.
Yeah.
Thank you for those questions. They were all very interesting.
Yeah. So yeah, that's the end of the question list, at least as it currently stands. So Mehak, I know we're almost running out of time, so I will hand it back to you for any maybe final thoughts or future considerations.
Thank you. Yeah, thank you everyone for attending the workshop. I still want to put this up there for any kind of emails or anything, any kind of way that you want to get in touch with me. We are always open to collaborations and any kind of question answer, or anything that you may have or any thoughts. I'm also looking forward to actually sending a survey of sorts to the attendees, because we want to hold more of these kind of workshops, and I just want to know what works and what doesn't. And this is especially interesting because it was a virtual, and I think one of the first virtual workshops in MGWR that was given today. So I would love to hear of any thoughts. There's no pressure, of course. If you don't want to fill out the survey, that's totally fine, but I would love to hear of any suggestions that people may have. So look out for that email, and everyone should also get the recording soon. Again, thank you for attending the workshop. It was really fun for me.
Yeah, and I would just add on to Mehak there that Mehak is too modest to say too much, but I think you did a great job on the workshop, Mehak, and I know that she and I are always looking for people who are interested in sort of playing with these ideas, trying to expand them further, and looking for future collaborations. So anyone who's interested in that, I'm sure Mehak would be more than receptive to look for opportunities to work with everyone as well. Though I don't want to put words in her mouth, but I think she would just be a little bit modest than she should be.
Thank you, Peter. But yeah, we're always looking for collaborations. That is very true. Yeah. So thank you for that.
Yeah.
Thanks to both of you for having this be part of the UCGIS Symposium. I'm sorry again that we're not now closing our computer screens and all heading off to the Hawaiian beaches for the rest of the day. But again, thank you for this. The response was very popular to it. We have we didn't know how many people, we didn't want to overwhelm the session today with all of the response, so we kept the size relatively small, and there's a long list of people who might like to take another instance of this workshop or something similar to it. Mm-hmm. So thank you very much. And thanks everyone else. We still have a few more sessions for the UCGIS Symposium, which wraps up tomorrow afternoon, or whatever time it might be in your local time zone. So check out the ucgis.org website for more information on that. And I look forward to connecting with all of you another time again soon. Thanks a lot. I'm going to close up the workshop now.
Thanks, everyone.
Thank you.
All right. Bye-bye.
Bye, everyone.
Bye.